Hello everyone. Last class we have discussed about torque speed and torque current characteristics of different types of motors. These motors were DC series motor, DC shunt motor, compound motors, etc. Torque speed characteristics of motor and load is to be considered to select a particular application or to run the load. Now during that period, some transient conditions are also seen, and these transient conditions are change in some of the parameters of the complete drive system at the time of starting, at the time of braking or running motor, plugging or reversing the direction of rotation of the motor. Now in these conditions, our system should operate economically as well as it should be reliable. So to consider those things, we should go for transient analysis of these motors. In this class, we will discuss about transient conditions in DC motor drives. So let's start. Before starting this one, let's see this DC series motor. In this DC series motor, torque speed characteristics already we have seen. This is nothing but the field winding of DC series motor, and the field winding is in series with the armature. So the same current flows through the field winding as well as the armature. Based on this one, some conditions we will derive, and we will conclude that torque is not directly proportional to the armature current, as we have seen in case of shunt or separately excited motor. So let's see, in series motor, flux is a function of armature current in unsaturated region of magnetization, or you can say linear region of magnetization, without saturating the core, or if we are operating our magnetic field in linear region of psi versus current characteristics, phi is directly proportional to armature current. So phi is equal to Kf into Ia. Kf is nothing but a field constant into armature current. Then the torque equation becomes T is equal to K motor constant into phi into Ia, and replace this phi by Kf into Ia. So it becomes K into Kf into Ia square. So omega m, or the speed of the motor, is derived as V by square root of Ke Kf, this is a constant, square root of T minus Ra by Ke into Kf. So here from this one we can draw the torque speed characteristics. At the same time we can conclude that torque is directly proportional to armature current square. So in comparison to separately excited DC motor, we can conclude here that if a small change in torque takes place, then increase in armature current is smaller in case of DC series motor. At the same time, we have seen that from the torque speed characteristics of this DC series motor, that at the time of starting, torque developed is very large. So DC series motors are very much suitable for applications where heavy torque is required, like in traction motors. And here it is understood that armature circuit resistance are now the sum of the armature and field winding resistance. So if you will consider Ra, that is nothing but resistance of this winding plus resistance of this armature winding. At the same time, we can see if the torque is low, then the speed is very high. So we can say that this DC series motor is not operated at no load condition. The transient analysis of DC machines, starting, braking, reversing, speed changing and load changing are the transient operations generally seen in case of DC motor drives as well as induction drives, or you can say complete drive system. Now starting, at the time of starting, motor draws more amount of current from the source. Now that current is to be limited, or suitable current limit controller is to be implemented in the circuit so that current should not exceed rating of the motor winding. The maximum current should not develop any sparking in the system or across the commutator. So commutators are nothing but it is connected across this DC machine to ensure that current always flows in the same direction in the armature conductors at the time of rotation of the motor. When the motor rotates at the time, current through the armature conductor should not change. That means direction of the current should remain same. Now for normally designed motors, 2 times the rated current can be allowed, but for especially designed machines it can be up to 3.5 times. Earlier also I have discussed this one. Then from the basics of this DC machines we know that at standstill when the speed is 0, at that time back EMF is 0, and the only resistance opposing flow of current is the armature circuit resistance, which is quite small for all types of DC motors. So at the time of starting, when the motor is at stationary, then EMF developed across this motor is 0. So if full voltage is applied across this one, then high amount of current will flow because the resistance of this winding is very low. At the same time, resistance of this one is also low. So less resistance is there to oppose the flow of current. So high amount of current will flow, and this may damage this field winding as well as the armature conductors. So suitable circuitry is to be connected to limit this starting current. As soon as motor starts rotation, then EMF develop across this motor, and the opposing force is now ready to oppose the armature current. Then slowly the current limiting arrangement can be removed from the circuits. So this we will discuss in detail with some example. Therefore, it is necessary to limit the current to a safe value during starting. Now you see, this is a traditional method to limit the current flowing through this armature current. This is a DC shunt motor. Here these resistances are there in the system. Initially at the time of starting, this switch S0 is made on and all resistances are in the path of this armature current to limit the current within safe way. Because of that small amount of current, here some amount of EMF will be developed across this armature conductor. Now this EMF will oppose this current, that means opposing force is developing to oppose the armature current. Now as soon as this EMF developed across the armature increases, then slowly these resistances are removed from the system by switching this S1, S2, S3 on. Then the current will be bypassed through this direction at rated speed of the motor. But this is a traditional way, and the disadvantage of this method is that lots of power dissipated across these resistances, so the efficiency of the complete drive system reduces. Nowadays there are many power electronics converters which can be used here to reduce these losses and increase the efficiency of the system. You can explore this one or you can discuss these things in power electronics portion. In braking, the motor works as a generator, developing a negative torque which opposes the motion. So to reduce the speed from the rated speed to 0 speed, generally braking is done. Now there are basically 3 types of braking: regenerative braking, dynamic or rheostatic braking, and plugging or reverse voltage braking. Now let's see this regenerative braking. So in regenerative braking, generated energy is supplied to the source. Whatever energy is developed at the time of braking or by reducing the speed from the running speed to the lesser speed or 0, then that generated energy is supplied to the source, and that can be also done with the help of power electronics converter. In detail we will see in case of induction machine drives. Now in case of DC machine drives, some condition is to be satisfied, otherwise this regenerative energy will not be able to fade to the source again. That condition is E must be greater than V. You can see here it is E. Now this one is V. Now if E is not more than V, then current will not flow in this direction, because we are saying at the time of braking we are reducing the speed of this motor. At the same time we are using this one as a generator, so the generator will supply power to this battery. So the direction of the armature current will change. At the same time, current will flow from this side to this side only if it is at higher potential. That means E must be more than V. So this condition is to be satisfied to apply regenerative braking. So E must be greater than V and IA to be negative. This is possible only in case of separately excited motor, because in separately excited motor this E is equal to Ke phi into omega n. Now this phi is controlled through a separate DC source, and this phi can be increased in such a way to obtain E more than V. Then we can feed the power to the source. Now important point of this discussion: for a source of fixed voltage of rated value, regenerative braking is possible only for speeds higher than the rated, and with a variable voltage source it is also possible below rated speeds. So if the source voltage is variable, then in case whatever E we have developed across the motor, then the source voltage is to be reduced less than E. That means power can be fed back to the source in case of variable voltage source. But whatever till now we have discussed, in that case we have not changed the input supply voltage V, but we have changed the value of phi. So if we are changing the value of phi, then it becomes speed more than the rated speed. That's why this statement is mentioned here, that it is possible only for speeds higher than the rated speed. In case of series motors, it is not possible to obtain E greater than V, because flux is directly proportional to the armature current. If speed increases, then armature current and therefore flux decreases. So it is not possible to increase E more than V. Dynamic braking. Here a separately excited motor is taken as example. In this case, motor is to be disconnected from the source and then connected across the resistance. So whatever generated energy is developed across this armature, it is to be dissipated across the resistance. So this method is generally used in case of low size motors or lower rating motors, because power generator is not too much, so that power may be dissipated across this resistance. But in case of large size motor, this is not the economical way. In that case, more amount of power will be dissipated or lost, so the complete efficiency of the system will reduce. So this dynamic braking is suitable for lower rating motors. So here in short we can say that if the motor is running at a particular speed and we want to brake the system, or we want to reduce the speed of the system to 0, then just remove the supply and connect that motor across a resistance. Then because of inertia of motion, whatever energy is developed across this armature, that will get dissipated across the resistance. So this is our dynamic braking. Plugging. Plugging is also possible in case of induction machines. At that time also we will discuss in detail. So here in case of DC machine, plugging means just reversal of direction of rotation of the motor, and when the speed becomes 0, at that time just remove the supply, then the motor will stop. So here in case of separately excited DC motor, this is separately excited field winding, this is our armature. Now the source voltage is reversed. So when the source voltage is reversed, then motor will try to rotate in opposite direction. So here you can say that negative torque is now developed. Now this voltage plus this voltage adds up and it will dissipate across this resistance. Ultimately, speed of the motor will come down to 0. Then if supply remains connected across the armature, then it will rotate in the opposite direction. If you want to stop that motor, then remove the supply when the motor reaches at 0 speed. Same thing can be achieved in case of DC series motor also. But here, no need to change the supply terminal, just change the motor terminal. It is easier to change the armature terminal. Then negative torque will be developed across this motor and the motor will come down to 0 speed. Then it will try to move in the opposite direction. But at that time, if you want to stop, just remove the supply. So this is nothing but plugging. So we have discussed about transient conditions in DC motor drives: starting, braking, then braking, regenerative braking, dynamic braking, plugging. So these are the different methods used in the system to bring the speed 0. At the same time, it should be ensured that current should not increase more than the rated current. In the next classes, few more things of this DC motor drives we will see. Thank you.